Welcome to Configuring the ScreenOS Firewalls. This is the session on VPN Concepts. So for the next 3 lessons we're going to be talking about IPSEC VPNs. This first one we're going to go over the standards-based IPSEC VPN process. The next lesson we'll see how that's implemented in the standard policy-based VPNs. And then in the third session we'll discuss the use of route-based VPNs, which are available on the Juniper product. So for starters, let's begin with the concepts involved in setting up IPSEC site-to-site VPNs. The objectives then for this session are to be able to define what a VPN is, a virtual private network, to be able to list the basic security concerns and how the VPN process addresses those concerns, to list the components that are involved in creating a VPN connection, and to explain the process that's used for IKE, Internet Key Exchange, which is a key portion of the VPN creation process. So all of these concepts are covered in this session. So this session's simply broken into 2 parts. We're going to go over the concepts and the terminology, and then we're going to dive into slightly more detail on how the IP security, IPSEC process actually works in creating a site-to-site VPN. So, beginning with the idea of virtual private networks. Historically, when you had multiple sites in an office and you needed to create a wide area network connection, we would get private circuits and we would get point-to-point connections to connect those sites. With the rise of the internet and ubiquitous internet access, IPSEC VPN was developed in order to create this private path between offices over a public network. So this secures private communication via what we call a tunnel between, in this diagram, the ISG 2000 at headquarters and the SSG 20 at the branch office, the tunnel indicated by that yellow piping that connects between the two. So we both have public internet access at both sites, yet we privately connect the traffic between the 2 sites. This uses a tunneling operation to create this, and the connectivity then for the private network is passed across that tunnel and hidden from the public network view. And while that data is transiting the public network, it is encapsulated in a way that secures it from the prying eyes of the public network. So there are 3 main concerns for security when creating this tunneling operation across a public network. You want confidentiality, so that your data is secure and not readable to anybody else who is using the public network. You need to maintain the integrity of the data as it transmits across the network, so that if packets and things are lost along the way, you know that, and that you know the reassembled data is accurate. So you need a way to check to make sure that everything arrived at point B after it's left point A. And then finally, you need an authentication method. You want to be able to confirm that the data you're getting, decrypting, and using is from who you think it's from. So you need to be able to authenticate that the arriving packets are from a source you want information from. So confidentiality, integrity, and authentication are the 3 big problems that IPSEC VPN is designed to overcome. So first we're going to talk about data encryption, the privacy aspect of this. It provides the confidentiality for the data that's transmitted. It is based on using a key architecture, so it uses a key to encrypt and decrypt. There are two types of keys that can be done. Symmetrical key, which means that the same key, symmetrically, the same key gets used to encrypt the data and decrypt the data. So that's like multiple people having the same key to a door. Everybody has the key, they can open the door. Asymmetrical keys is a different key is used to decrypt the data than is used to encrypt the data. This is often referred to as a public key architecture, and it uses a public-private key exchange. So the person encrypting the data has their private key that they and they alone have, and there's a public key. The public key is passed out freely to people that it wants to be able to decrypt his data. Anybody that has the public key will be able to decrypt data that was created with the private key, but they won't be able to pretend to be the original person. You cannot use the public key to create data. You can only use it to read data. So this provides a way to prevent people from forging information who you are by having a public-private key exchange. So by its nature then, this whole key architecture is a reversible process, and it has to be, because if you can't reverse the encryption, then you can't use the data. So symmetrical key encryption, this is a pictorial example of that. We have data on the left-hand side. It has a key on the top. So the data comes in, we apply the key to it using a mathematical algorithm and encrypt it. We pass the encrypted data across, and then the other side has the same key and is able to use that key by applying the reverse mathematical algorithm and get the raw data back out again. This is the fastest method for bulk encrypting data because it's a straightforward mathematical operation that has just one possible outcome, so it's very quick. And the typical key sizes that get used in symmetrical keys are anywhere from 40 to 1024 bits of data for encryption. And the methods that use this are DES, triple DES, and AES. So these are symmetrical key encryption algorithms. Now, here's a pictorial example of how public key encryption works. So we have a site A and a site B. In this case, the private key for B is on the left, and the private key for A is on the right. So we have site A on the right, site B on the left. Site A gives his public key to B, and B gives his public key to A. So you have two keys on each side. And then you use your private key to encrypt data, and the other side will use your public key to decrypt data. Since we both have keys, this can work in both directions, and the data will be encrypted differently going from A to B as B to A. But both sides can read each other's because they've exchanged their public key. The public-private key pairs are mathematically related, so that you can do a math operation using the private key to create the encrypted data, and you do a related math operation using the public key to decrypt it. And the reason that works is because there is a relationship between the public and the private key. This is because it involves two different keys and two different types of operations, it's slightly slower. for a lot of bulk encryption. The typical size of these keys are anywhere from 512 to 2048, so you can see another reason it's slower is the larger key sizes available. And examples of what uses this are RSA and DIFFIE-HELLMAN, DH, use public-private key exchange. Another example would be your SSL certificates are based on public-private key exchanges. Okay, so moving on to data integrity. We've encrypted the data, we've kept it private. Now we're going to talk about ways that you can make sure the data is correct when it's decrypted. These are basically done using hash functions to confirm that the output of the decryption algorithm matches the input on the other side. So one-way hashing is generally the method used here. When you have a hash, you cannot necessarily determine or you cannot determine what the original data was. It's just verifying that the original data matches what was originally sent. So in the old style world, we used to do this with checksums and be able to do a math. You're doing a math operation on the data, checking it against the hash value and making sure that the values are the same and therefore nothing has changed inside your data. These are designed with fixed length outputs so that the mathematical operations can happen very quickly. And examples of methods that utilize hashing for data integrity are MD5, SHA-1, and SHA-2. And as you can see going down the chain there, each one of them becomes larger in the hash value as we go down the chain. So the point of these operations when you're selecting MD5, SHA-1, and SHA-2 is to verify that the data you've decrypted is a match to what has been sent to you. So a quick look at one-way hash algorithms. You cannot determine the data from the hash value, so you can't use the hash value to bypass your encryption. It's merely a check to make sure the data is accurate. They have to be collision resistant. Collision resistant means the mathematical method you use to generate the hash value has to be unique for any data value. If the math operation can generate the same hash answer for two different data values, then that's a collision. And that would mean you could potentially get a hash that says the data is accurate when it isn't. So the math that's applied has to be done in a way that there's one and only one hash answer for the operation that's performed. How does this process work? When the sender gets the data, he will create, the sender side will create the hash before encrypting the data. So that's the hash from the actual data. Then the sender will append the hash value to the data that's being sent. So the receiver knows what the hash answer should be when they perform the mathematical operation. The receiver will separate the hash from the data, and then the receiver will take the data and do the math operation again to create a hash answer of its own. And then the receiver will compare those two hash values, the one it received from the original transmission, the one it generated by doing the math itself, and make sure they're the same. If the two hash values are the same, then we know the data is intact and has not been damaged at all by the transmission process. Okay, moving on to the third concern. We want to make sure that the data we're receiving is from the source we expect it to be from and not from a bogus source trying to insert data into our network. Source authentication. This is going to validate the sender of the information to make sure it is the other node in our network. We are using HMAC, hashed method authentication code is the method that IPSEC uses for this, HMAC. And this can also be used with a pre-shared key. This is a secret value that administrators will manually put into their configuration, and you'll see where that happens when we do the configurations on the ScreenOS devices. And this is a value that has to be exchanged separately from the network communications that are involved in creating the tunnel. This is an additional security, so you generally exchange this value via the phone or some other secure offline method so that this value, this pre-shared key, cannot be intercepted by anybody. And so this provides an extra layer of security in this authentication. If you don't know the pre-shared key, you cannot authenticate the source. Okay, this is the data integrity model using HMAC to authenticate your source. The sender is going to append the pre-shared key to the data before beginning the process. Then it's going to create a hash based on that combined data set, the data plus the pre-shared key. Then the sender forwards this data and the hash to the receiver. Now the receiver knows the pre-shared key, so it appends it to the data and creates a hash. And then it compares to see if the hashes match. Now, because the pre-shared key value never transited the network, the original source A appended the pre-shared key to the data, did the math, created the hash, removes the pre-shared key, and sends the data. So the pre-shared key never transits the network. It's up to the receiver to put the key onto the data and do the hash again and compare. So this value of the pre-shared key never goes across the wire and must be known by both sites in order for the algorithm to check out, and therefore we know that the data has come to somebody with this secret knowledge. Okay, there's if we're using keys, which we are for this encryption process, they have to be exchanged between the two devices. So for both the encryption and the hashing, we need the key values, either the public-private pairs or the symmetrical key. This can be done with manual configuration, the same way we do with the pre-shared secret. This was an original method. It's very, very rarely used anymore, and it requires that the key values be manually keyed in on both sides. A further disadvantage of this, it's easy to make a mistake in keying in these large keys, but a second disadvantage of this is they don't change then. In order to change them, you both have to log in and you both have to change them. So they stay in place for a long time. The more common method now is automatic key exchange, and then the devices themselves will automatically generate their public and private keys. They will exchange their public keys over the network, and then they will change the keys. They will agree to change the keys periodically during the tunnel lifetime. So it's a very secure method, constantly changing the encryption as the tunnel is being used. DIFFIE-HELLMAN, key exchange algorithm is how this is accomplished in the standards-based process. So this uses public key cryptography, a public-private key pair, and it distributes these key pairs, the public, between each device as part of the process. Only that public one will transit the network. Each side will keep its private key for its encryption process, and it will only share the public key across the wire. Diffie-Hellman is set up in 5 different groups, and the mathematical algorithm is based on large prime numbers and a generator. So each of the groups represents a different prime number size. So you have group 1, 2, 5, and 14. And as you can see, as you go down the group structure, the size of the prime number and therefore the strength of the encryption increases. The only thing that's important to remember about this particular thing is that the group has to match on both sides of your tunnel. You have to agree to a group process for the negotiations in the tunnel to come up. So you both have to use group 2 or whatever you decide. Okay, let's take a look at how some of these concepts play out in the implementation of the IP security, IPSEC process that is standardized. IPSEC is an industry standard for security and integrity of passing data. So these IPSEC VPNs are standard. They're implemented in multiple platforms by any number of companies that create VPN-enabled firewalls. The whole process works based on the IP layer of network communications, and it is supported in unicast traffic. So in order to do multicast or other items across an IPSEC VPN, you generally have to have other items configured for this to work. You know, GRE or the route-based VPNs of the Juniper product. The standards-based IPSEC VPN is strictly for unicast IP traffic. It uses 2 protocols to establish the IPSEC, ESP and AH, to handle all of these security concerns that we've gone over in the first part of the session. There are 2 modes for IPSEC. Transport mode is that which is used for endpoints like servers or computers and the original IP packet is handled by the device itself, then remains intact in creating the tunnel. And in tunnel mode, which is more typical in the firewall environment, you're doing a device-to-device encapsulated tunnel. So the items behind you are not aware of what's happening. It's all being handled by the endpoints in this, and the endpoints are creating new IP packets that are encapsulating everything that's being generated by the devices behind them themselves. Let's take a look at ESP. ESP can be used in either tunnel or transport mode. It provides confidentiality, integrity, and authentication. All 3 of the concerns are covered by the ESP operation: confidentiality, integrity, and authentication. It can also handle anti-replay to avoid the tunnel being hijacked and items being injected into it, and it is defined in RFC 4303. This operates on IP protocol 50. So these are the characteristics of ESP. Authentication header, AH, it can also be used in both tunnel and transport mode. There is no data encryption in AH operations, so it does not handle the confidentiality portion. It also cannot operate if it's behind a NAT device if you're using the transport mode. So this method will not work behind a NAT device when you're in transport mode. It does handle data integrity, and it does handle authentication, or else they wouldn't call it authentication header. So it handles 2 of the 3 concerns, and it has some limitations. This also allows for anti-replay to be in place. It's defined in RFC 4302, and it uses IP protocol 51. Okay, looking at the tunnel mode packets, this is how these are encapsulated and put together in a payload on IP. You'll see a new header that gets added to the front of it in both AH and ESP, and you can see in ESP mode the authentication applies just from the ESP header through the payload, and the payload itself is encrypted. Whereas in the authentication header, the entire packet is able to be authenticated as valid, and there is no encryption on the payload. Internet key exchange, IKE operations. So let's see how the key process works in IPSEC. This is all based on creating security associations, SA. This is the keyword that happens when we provide after the key exchange is successful. They negotiate a proposal back and forth for both the encryption and the authentication. They make sure that all these settings we've just talked about are agreed upon and match. They create then the encryption and the authentication keys on both ends and set up the time when they're going to automatically refresh those keys based on the lifetimes. And then they're going to provide a way to identify the gateway so that we know this is a gateway we want to accept information from, and that we're associated with. So a security association is connected to the gateway, and not any other gateway. So they have to match. This runs on UDP port 500 for the IP connection operations. In version 2 of IKE, Internet Key Exchange, this is covered in RFC 4306. This allows for different negotiations at each end of the tunnel instead of all of the security associations having to be the same. It is able to be more resistant to denial of service attacks that are aimed at IKE protocol, and it provides support for EAP, extensible authentication protocol, for security, and it's able to connect in fewer messages to establish the key exchange and get the tunnel up and operating. Obviously, if you're using an IKE1 or IKE v2, it has to be set up the same on both devices that are creating the tunnel. So the security associations, the SAs, these are a set of policies and keys then that are exchanged between the peers. This will tell each of the peer firewalls what networks or hosts are allowed to communicate with each other. It provides a unique set of attributes, the destination IP address, the security protocols that are going to be used for this whole transfer operation, and it generates an SPI, which is an internal index number that shows the association's relationship to the gateways and protocols on the box. So the SPI is used to make sure that the packets coming in are matching an SA that's set up on the device and active between two hosts. The SA establishes with IKE phase 1 and phase 2 and is associated with those negotiations. Phase 1 SA is bidirectional. So when the phase 1 goes through, they exchange messages and they're able to pass traffic back and forth. But phase 2s are unidirectional. So you are essentially creating, if you want traffic to flow in both directions, you're going to have an SA going in each direction, and we'll see how you identify those in the ScreenOS. Once an SA is created, each device has to maintain a database of their security associations. So each site keeps a record of what SAs are active so that it can compare and associate the arriving packets from the multiple IPSEC VPNs with the correct security association. The command to see what's active on your ScreenOS device is get SA. That's going to return the list of all the security associations that are up and running on that device. PROXY-ID is a locally generated phase 2 IKE ID. These are used to identify the SA for the VPN, and they are also used as like a preliminary access control list for the remote and the local network subnets. You can have multiple proxy IDs involved in an IPSEC VPN tunnel, and what they do is identify the remote and local networks that are permitted to talk to each other. So there's two values in these. They come in pairs. You often hear them called the proxy ID pair. You have the local proxy ID and the remote proxy ID. So in order for the security association to complete, these proxy IDs have to match. The local on my side has to match the remote on the other side, and vice versa. The remote on my side has to match the local on the other side. The proxy ID pairs have to match, or you'll see an error in the log. These can also be used then for policy checking in order to permit or deny traffic. If you want to allow everything across IPSEC VPN, then you would use 0.0.0.0/0 for the local and remote proxy ID, and then if both sides accept that, then you're allowing at the base level all traffic, and then you're controlling the access controls by your configured policies on the device itself. Not every vendor will allow that to be used as a proxy ID, so sometimes you're restricted in being able to do an any-to-any IPSEC security association. Okay, phase 1 of IKE There are two peers will establish the authenticated channel between the gateways. This will use the Diffie-Hellman key exchange process. There are options on how the negotiations occur. You can use main mode or aggressive mode. Main mode is used when two peer devices have static IP addresses, and aggressive mode is generally used when one of the devices has a dynamic IP address. So if you're doing like a computer to firewall VPN connection, it would be done in aggressive mode. In IKE version 2, there's a change in the naming conventions. So we have IKE SA init and IKE auth as the names that you'll be seeing in the logs for these negotiations. Phase 2, after the gateways have connected, we'll negotiate the security association using that phase 1 channel. The PROXY-ID pairs will be identified and compared. And this will also use Diffie-Hellman to exchange the keys to encrypt the traffic. There is a this is referred to as quick mode for phase 2 negotiations. It takes only 3 instead of 6 exchanges to complete phase 2 as opposed to phase 1, so hence the name. And IKE v2, again, there's a name change. You'll see this create child SA if you're using IKE v2 to identify these in the log. Okay, so if we're using main mode on phase 1, these are the exchanges that'll occur. In the first exchange, we have our cookie and the SA proposal list will be sent by the initiator. The responder will accept send a cookie response and a proposal acceptance. So those are the first two messages. The next 2 messages, then the initiator will send back the DH public key value and a random number, and the responder will respond with their public key value and a response to the random number to say that everything's accepted. And then the last 2 messages are to create the hash and identification to complete the negotiation process. So there's 6 messages exchanged in main mode in order to bring up the phase 1 of IKE. In phase 2, quick mode, then to bring up the rest of the tunnel, the initiator will send its first message with the phase 1 information and the hash and giving the key and the proxy IDs. The responder will return with message number 2 to confirm this information and send their own key and proxy IDs. And then in the third message, we do the hash and compare for phase 1, and then we acknowledge that everything's correct, our proxy IDs have matched, and the phase 2 comes up. So now we have our completed negotiation, both phase 1 and phase 2, for our IPSEC VPN. If we're using aggressive mode, because we have a dynamically addressed peer on phase 1, there is a change then in the process. There's a different message in phase 1, and there's only 3 messages exchanged. So the initiator is going to be the dynamic side of the pair, providing the proposal list and the key and the random number. The firewall will respond to this request, and then the initiator will send the hash and the ID and the key, and in aggressive mode then phase 1 is complete after only these 3 exchanges. Summarizing our IPSEC tunnel, phase 1 creates that gateway-to-gateway connection. Phase 2 creates the security association and exchanges the initial policy set. And then the data flow at that point is fully encrypted. So this is our basic establishment of the IPSEC VPN tunnel. Any of these technologies that we've mentioned along here that don't match between the 2 pairs will generate error messages in the log. So 90% of the time when your IPSEC VPNs don't come up, you're going to go to the log and you're going to see those terms: mismatched proxy IDs, proposal not accepted, no gateway available for that proposal. These terms will show up in the log, and they'll be telling you which one of those elements is not matching between the 2 sites. Okay, so now we're going to take a look at the packet handling once this tunnel is up and running. At the originating site that's generating the traffic, the packet will arrive. The route lookup will indicate that it has to go up through the tunnel. It will check the policies for that tunnel and make sure this is permitted. If it is, it will then encrypt it, hash it, and prepare it for transit across the tunnel and send it over. On the receiving side, this will then receive the encrypted packet. It will make sure the SPI matches to their SA database so that it's a valid connection coming in from another site. It'll check the hash and make sure that the data has survived the trip across the internet. Decrypting the packet does its own policy check to make sure it matches what's allowed on their side, and then it will forward it out to the receiving device. So very straightforward, step by step, but as you could see, there was a lot of detail under the hood in making that process happen. So in this session on the concepts of IPSEC VPN, we've defined what virtual private networks are. We've listed the security concerns and how the protocol addresses the security concerns and being able to transmit and receive data across a public network instead of secured private lines. We've listed the various components that are involved in addressing those concerns and how they interact with each other. And we've explained the process of internet key exchange for creating an IPSEC VPN between 2 firewalls. If you have any questions about these concepts and materials, feel free to post them publicly in the forum associated with the class, or to respond to your fellow students' questions that are in there. If you'd like to contact me privately about the material presented, go ahead and use the contact information on the class website, and I'll get back to you as soon as I can. I thank you very much for your kind attention to this session on the concepts involved in creating IPSEC VPNs.